Hello! Node can be used to write programs that do just about anything, from parsing files and exploring astronomical data to even making games. But whatever we're making, Node is almost always used to bring our programs to the web by building backends for websites and mobile applications which share the data for our astronomical observations or games or whatever it is that we're building. And that's what we're going to start making in this section. But let's be clear. What is a backend, a web server, or an HTTP server? And how do all these things work? Let's expand slightly on the model that we introduced earlier in the course. When you type something into your browser, say you're going to a site like facebook.com, your browser actually starts by calling a system called DNS, or the domain name system. It uses DNS by talking to DNS servers across the internet. These servers look up the internet address of the server given the name, the URL that we've typed into our browser. This is a bit like Google Maps, looking up the address of, say, the Empire State Building in New York. We give Google the name of what we're looking for, and it gives us the actual address where that object lives on West 34th Street. Except instead of street names and numbers, on the internet, our addresses are what's called IP, or Internet Protocol addresses. And this IP address is what the DNS server sends back to our computer. It's usually a set of 4 numbers between 0 and 255, which are separated by periods. It's this IP address that we then use to communicate with the server, which will give us the data that we're asking for. It's an HTTP server because we communicate with it using this HTTP protocol, the Hypertext Transfer Protocol, or the secure version of that, which encrypts our communication so that no one can snoop on or steal our data. We could have servers that use other protocols, for example, to handle emails. And the way that we specify which type of server with which application we're talking to is by adding to our IP address this port number, which comes after the colon character. The port specifies which application on that server should handle our request. So in this case, we have an HTTP server running on port 80 that will then send back to our browser whatever data that we need to display. Especially if it's a dynamic website like Facebook with changing content. The server often sends back data like JSON files or text, maybe images or videos. All right, I know we're talking about a lot of different terms, but we're going to apply and experience all of this using Node in this section, and it'll all be clear by the end. And in fact, as developers, we often don't have to worry about DNS because the browser and our computer manages these mappings of site names or URLs with IP addresses for us. And it only makes the request to the DNS server the first time we browse to that site. Afterwards, storing the location in what's called the DNS cache, which saves us some work and improves performance when we're browsing the web. It's pretty clever. All right, let's dive into this HTTP section and apply what we've learned in the coming videos. I'll see you then. Welcome back. We've seen how when we browse to a site, we use this system called DNS to figure out where that site lives, which IP address we should use when communicating with it. And we can then make requests to our HTTP web server to get data back from it. The thing that defines how our web server responds to these requests is our API. The API tells us what kinds of functions the server should support and how those functions should be used. Functions like, for example, getting a list of your friends, or getting their messages or photos. We can implement our API on the server in Node, in Python, or any other programming language. What matters is that the language that we use when reacting to these requests and responding to them is HTTP, which is the common way that the browser and the server can use to understand what both sides are saying. So the browser is speaking HTTP to the server, and the server can respond because, again, it's speaking HTTP. So what does this language look like? What are the words that HTTP uses? For that, we can browse to my favorite site in the world, the Mozilla Developer Documentation, which has this excellent reference for the HTTP request methods, which are also sometimes called the HTTP verbs. They represent all of the possible actions that you might want to perform on the server side as a browser. So a browser might want to get some data or a file that's stored on that server. It might want to post some data, which is another way of saying to submit or send something to the server. Maybe a message or a photo that you want to upload. Or maybe you want to delete some data that the server has about you as a user. And there's a few more methods that HTTP supports that are less commonly used, but we'll go over them when it makes sense to in the course. But this is pretty much it. We can see all of the available HTTP methods, all of the words in the HTTP language that you need to learn to build the app of your dreams. HTTP has become the language of the web because it's so simple. So in the next video, let's take a look at the kinds of messages that we can send and receive in HTTP using the methods that we've seen here. I'll see you soon. Welcome back. What kinds of messages do we send back and forth in HTTP? What does an HTTP conversation look like? Remember that an API stands for Application Programming Interface. It specifies how two applications talk to each other. For example, a browser and a web server. And on the web, generally, it's the browser making requests and the server responding to those requests. If you think of an API almost like a set of phrases in a language that you can put together to communicate an idea or to get some work done, then it's generally the browser that starts that conversation and asks questions of the server, waiting for its response before potentially making another request. It's almost like the browser is interviewing the server. So, what kinds of things can we ask of our web server? Well, with HTTP, our API is made up of operations using these methods like get and post, which we saw, that are used on different collections of data. Like, for example, a list of friends, or messages, or photos. We can combine the name of the method with the collection name to get the data that the server has on who our friends are. Or we could add an ID after the name of our collection to specify that we want to get the data about a specific friend, who in this case is identified by the number 5. We can generally categorize our requests into those that are being made on collections of data and those that are being made on specific items in those same collections. This applies to all of our HTTP verbs. So we could also post to our messages collection if we wanted to save a message and send it to our friends, for example. We would use the post verb and attach the contents of our message to that request. But in general, it wouldn't make sense for us to try to post to a specific message because we generally only add to collections and not to individual items. So let's not do that. But it is possible for us to want to update a specific message, to change some text, or add a photo. And so for that, we would use a put request, which allows us to replace the message that we specify with the message that we pass in through that request in what's called the body of that request. We might decide that we're no longer happy with our message and want to delete it. Or maybe someone is unlucky enough that you want to remove them as a friend. These are all possible HTTP requests. Every one of these requests has 4 main parts that it's made up of. The first is the method, which, like we just saw, can be something like post or get, that defines the operation that the browser wants to perform on the server. And we've also seen that each verb is matched up with a path to a collection or a specific item of a collection. This path is also sometimes called the resource that we're accessing on the backend. And I briefly mentioned that we can send data to the server by adding a body to our request, which contains the data that we're sending from the browser to the server. This could be in plain text or in a variety of other formats. But the most common format for sending data back and forth over HTTP is JSON, which is what we're going to be using for this course. And for a message, it might look something like a property that specifies the message itself and maybe a photo where you specify the path of the photo file. usually will have a body on POST requests and on PUT requests, where we're updating some data on the server, but not on GET or DELETE requests. Because for those operations, the server knows everything it needs to from just the method and the path, and last but not least, the fourth part of every single request, which is the headers. These are optional properties that you can specify on a request to send additional metadata to the servers. That is, data about the data that you're sending, data about the request. So things like the size of the data that you're sending, or any authentication information that you need to send so that the server knows that you're allowed to perform that operation with your user. These are optional depending on your use case, but there's one header that every single request needs to have. Can you guess what it is? It's the host header, which specifies which server your request is being sent to, including sometimes the port number for that site. The host needs to be specified to verify that you're sending your message to the right server. But that's pretty much it. Using these few parts, you can send over any request you can imagine over to the server so that it can respond to your request. And we'll find out all about the responses from the server in the next video. So I'll see you in the next one. All right, we've seen how the browser sends messages or requests to the server by passing in the method, a path to a resource or collection, sometimes a body with some data to send to the server, and an optional list of headers with metadata about that request. Now, what does the server respond with? Responses in HTTP are even simpler than requests. We have three main parts. Just like the request, we have an optional list of headers. Things like the content type, which is a header that you might see in both a request and a response. That tells us the type of data that's being sent in the body of the request, if it's a request, or in the body of the response, which means our second main component of a response is the body that contains the data that you're fetching from the server. And if you've set the content type as application JSON on the server side, that means that the server is sending a JSON object. Say it's a message from the messages collection that's telling us hi. So far, the response seems to be fairly one-to-one with the request. Both have headers and both have a body. Where a response differs from a request is that it includes a status code, which tells us whether the request was successful, and if not, it gives us an error code that generally tells us what went wrong. The status code that you want to see is 200, which indicates that the response is a successful one. But there's a few more possibilities. Every possible HTTP status code can be put into one of 5 groups. The 100 series responses, the 200 series responses, and so on, all the way up to 599. Let's see some examples. The 100 series group has information responses that you generally won't see as a developer. These are used internally by libraries and browsers when, for example, you're sending a large request and you need to indicate that everything is okay and the requests can continue. For successful responses, we've already seen that the standard is this 200 OK, which is a general way of saying that a request succeeded and a response is available. But we can also be a little bit more specific. If we're submitting information to the server using a POST or PUT request, the most correct response is a 201 created. Now, in some servers, you might see 200 responses for PUT and POST requests as well, but it's best to be as specific as possible. And you'll generally see this trend where the 00 response, the first one in that series, is the generic one, and then the ones after it, like 201, are the more specific variants. So let's see what the 300 status codes can be. These are redirection messages. And the most common one that you'll see is a 301, which means that some URL on the internet, on a server, has been renamed or moved, and you should instead be going to the new URL, what will be provided in that response. And scrolling down a bit further, we have the client error responses. This means that the browser or whoever is making that request made that request incorrectly, and the server isn't able to respond to it. So we have the 400 bad request response, which is just a general catch-all error if, for example, the inputs that browser is sending on a form don't match up with what server expects or needs in order to process that data. But we also have these more specific responses. The ones that we'll use most often include 401 unauthorized and 403 forbidden. These are two error codes that are often confused, and I know I get them confused sometimes as well. The main difference is that with 401, the server is saying that you're not authenticated, or you're authenticated incorrectly, which most often means that you're not logged in. And the server is telling you to log back into the server, into the website, and try that request again. The 403 error is more permanent. The server is saying, I know who you are, and you're not allowed to access this data. You don't have permission, and don't bother me again unless something changes and you get more access. So with the 401, you're not logged in, and with the 403, you are. All right, and after 403 comes the status code that everyone knows. 404 not found. As developers, to us this means that the URL that we're trying to access from the server is pointing to a resource that doesn't exist or that the server doesn't recognize. So maybe we're trying to access a collection that doesn't exist or a specific item from that collection, which might have been deleted in the past. And we might also see method not allowed, which means that a collection exists, but maybe we're not allowed to post data to it. So we get this status code when the method we're trying to use is not supported. And we might also see request timeout, where a server is saying that that request took too long and is no longer valid. There's actually quite a few other 400 series status codes that you might see depending on how specific the server that you're working with wants to be. You might even come across the most rare status code of all, which was added by the people behind HTTP as an April Fool's joke. If we scroll down to 418, we see a status code for, that's right, I'm a teapot, which is a natural response when you try to brew coffee with a teapot. Just a little bit of HTTP humor for you there. And so we can also scroll down to the 500 errors. These differ from the 400 series status codes in how they represent that while the request that's being made was valid, something went wrong on the server side. Whereas 400 errors mean that something's wrong with the request and the data being passed from the client to the server. The 500 errors mean that it's the server that's at fault. So we have the generic 500 internal server error, which you might get if the server crashed. But we also have these more specific codes. So 501 not implemented is something you might see on APIs that are currently under development, where your request might be valid, but the server just isn't ready to respond to it yet. Maybe it never will. And the last most common server-side error is this 503 service unavailable, which is used for when there's a temporary issue on the server side that's causing it to be unavailable. For example, there's too many users and it's just not able to handle all of that load. All right, I wanted to give you a summary of some of the more common HTTP status codes, because being familiar with them helps in both front-end and back-end development. It helps to understand some of the scenarios that we can experience when writing server-side code. And also because we're going to be using them when we start writing our own servers. So before we move on, let's really solidify what we've learned and look at a request and response in action by going to our developer console here in Chrome. I'm going to go to the Network tab and refresh the Mozilla developer documentation. We can see all the requests that are being made for this single page, including the Mozilla icon. And if we scroll up, the actual HTML page that lives at the URL we're browsing. So we can see that we're making a request to this HTTP status page under the developer.mozilla.org domain. We're making a GET request, and in response, we've gotten a successful 200 response. The server is located at this address with the IP on the left and the port number on the right. And if we scroll down, we can see the headers of the response, including that content type, which in this case is set to HTML. And scrolling down, we can see that we also have the headers of the request with various additional information like our cookies, which we'll talk about later in the course, but also things like the user agent, which tells the server about the client that's making the request. So in my case, the browser, Chrome, that I'm browsing the developer documentation with. And if we wanted to see the actual body of the response, we can go to the Response tab here to see the HTML for this page. And we can do this for every request that our browser makes. So open your developer tools, go to the Network tab, browse to your favorite sites, and experiment with what HTTP requests are being made. You can really learn a lot about the web by doing just that. And I'll see you in the next video. Welcome back. We're about to reach a big milestone in our knowledge of Node. It's time to start making Node servers that we can put on the web to handle requests from users. Users who are using web browsers and mobile applications to talk to our server. And we're going to start in this fresh HTTP server example with a blank index.js. The first thing that we're going to do is import this HTTP module. Node includes this core HTTP module, which allows us to make requests, to respond to incoming requests, and to work with different types of content. The first thing that we want to do is to create our server, which we can do by calling http.createServer. And that will give us this server object that we can use to, for example, start up that server. And this createServer function expects a callback, which is what's called the request listener, that basically tells the server what to do when it gets a request. So our callback function takes in two parameters: the incoming message, which we call rec, and the server response that we're going to send back to whoever made that request. And we call that the res. So let's do that. We take in the request and the response. Now, what can we do inside of this request listener? Using the request, we can look into the headers and the data that were passed in from the client. And using the response object, we can create a response by writing some data and headers to send back to that client. This is where things start coming together, because both the rec and the res objects are streams, just like the ones we saw in the planets project. The request is a readable stream, which we can listen to for data coming in through that stream by using the .on function. We'll see that in a bit, but the res is a writable stream. And so, say we wanted to respond with a success message, we could use the res.writeHead function to write some headers to the response. So the first parameter here is the status code, which is going to be 200 for a successful response. And then we can pass in this object with a list of all of our response headers. For now, we're going to set the content type of the data that we're passing back to the browser. And in this case, let's start with just some plain text. And if that's how we set the headers, so we've done res.writeHead, how do we set the data to pass back to the browser? We can use this res.end function, which is called end because it signals that the response, including the headers and any other data that we want to pass, is now complete and ready to be sent back. So this end function needs to be called on each request that comes in to the server, even if it's empty. But in our case, maybe our server is telling us about our friends, and maybe it wants to pass back this plain text that says, "Hello, Sir Isaac Newton is your friend." Remember him? The one who basically discovered gravity and invented calculus and physics and all of your other favorite subjects? Or maybe that's just me. I don't know. Well, now our server is set up to always tell us that Mr. Newton is our friend. But we're not quite done yet. We still need to tell our server to start listening to requests, which we can do by calling this server.listen function. Now, our server will by default listen on our local machine. And our local machine doesn't have a domain like google.com set up for it. But we do have an IP address, which is usually something like 127.0.0.1. That's your local machine. But because these numbers aren't that easy to memorize, your machine has a default name, which is localhost. We can access any server running on our machine by using this localhost in, for example, our browser. So that's already set up for us. But what we do need to pass in through our listen function is the port number that our server is going to be listening on. Because we can have different applications running on our local machine or on any server, and the port number is basically used to direct traffic coming in to the right application, to the right server on your machine. All right, so let's set up a port. We're going to say const port, and by default, you'll often see numbers like 3000 or 4000 for web servers in Node. So we're going to use that, and we're going to pass in port to our listen function. And the function also allows us to pass in a callback, which is run when the server starts listening. So we're just going to console.log for now that we're listening on port 3000. So passing in that number, which we're passing in here as a template string. All right, so let's see if we've done things correctly and run this server. Looks like things are working, and it's listening on port 3000. Now, in our browser, we can go to localhost using the address of our local machine and port 3000, and check it out. We get our message. Our browser has made a request and received a response from our Node server. But what if we wanted to return other types of data? Say we wanted to return a JavaScript object instead of this text. Well, that's what this content type is for. Rather than plain text, we can set it to the content type for our JavaScript object notation, which is application/JSON. This allows us to now pass in a JavaScript object. Say we're passing in the name of our friend, which remember is Sir Isaac Newton, and maybe we're giving that friend an ID. So what we need to do before we send this data back to the browser is to turn it into a string, which is what this res.end function expects to be passed in. And that's what our JSON.stringify function is for. we'll pass our object directly in to be stringified. That's about it. We can now pass back any JSON object with whatever data we want to send to the client. And we could do the same thing for any other content type. Let's test this out. Let's restart our server. And now in our browser, if we refresh the page, we're getting our JSON object. See how easy that is? We're not even using any fancy third-party modules or frameworks that create our server for us. This is all built-in Node functionality. But how do we respond to many different types of requests, all in one server? How do we deal with incoming data? Let's find out. I'll see you in the next one. Welcome back. Our current server always responds with the same thing, with our friend Sir Isaac Newton. But normally, we want our servers to be a bit more dynamic than this. We want them to respond to different types of requests depending on some logic that lives in the server, with different URLs representing different types of requests. Our Node HTTP server that we're creating is an event emitter. When we're passing this callback here, remember how I called it the request listener? Well, that's because when we write this, it's actually shorthand for writing server.on request and then passing in our callback. However, our server isn't giving us different events for requests made against different URLs. I can make requests against localhost on port 3000 and pass in any URL, like let's say Mars, and the very same function that request listener will respond. It doesn't matter what I put. When we have a server that has multiple different URLs that respond differently depending on which one is being requested and with what HTTP method it's being requested, in that case, we call these different URLs endpoints. This is a term that you'll hear often when working with servers. Each different URL that you can hit is an endpoint that's responsible for a specific piece of functionality that's provided by the backend server. So what does this look like? How do we make different endpoints for our HTTP server? We do this by looking at the request coming in, and specifically by checking the request.url and seeing if that matches the endpoint for our functionality. So we can say for our friend's endpoint, we're going to do what we did down here and return our friend's data. And if we get a request matching a different URL, say the messages collection or the messages endpoint, we'll do something else. Maybe we want to send our messages as HTML instead of as JSON. And because HTML can get fairly long, we'll use the response.write function to write our HTML code piece by piece to our stream as text so that we don't have to put it all in one res.end function call. So maybe I'll do a few different messages in an unordered list in our HTML. Maybe our first message is, "Hello, Isaac." And our second message is, "What are your thoughts on astronomy?" And now we'll close out our tags. And then tell Node that the response has been written and we're no longer going to be writing to that stream. Writing out HTML in this way can get pretty tiresome pretty quickly. And so we're going to improve upon this greatly. But this demonstrates how we can send different types of content out from our server. And we don't need to set the status code because if we don't set it, it defaults to 200. But you might see the headers written in this convenience syntax in some HTTP servers. Instead of using the write head function, you can optionally use res.statuscode and set that directly. Plus, for headers, you can set them individually using the setHeader function, passing in the name of the header, so content type, and then the value of that header. These two methods are basically equivalent. And so we can use this setHeader function to set the headers for our HTML response, setting the content type to text/HTML, letting the browser know that what we're sending should be rendered as HTML. Okay, we've written a fair bit of code here. Now it's time to see our endpoints in action. Let's run our server, and in our browser, let's see what happens if we go to list our friends information. All right, we're still getting the same JSON object, but what happens if we get our messages? Check it out. We're getting HTML that's being rendered in our browser based on data in the server. The browser understands the different types of data that the server might respond with depending on which endpoint we're hitting. But what happens if we type in some non-existing endpoint and try to get the data from our server? We don't really get a response. What we should be getting is a 404 not found. And the good news is that we can add this functionality without much code. Our server will tell us that the page wasn't found if none of these other endpoints match. So in this else condition, and we'll just set the response status code to be 404. And we always need to remember to call that end function. So if we run this again and go back to the browser, I can type a URL that doesn't exist, like Mars, and we get this 404 error that our browser understands, while it still responds to our other endpoints correctly. Our server is starting to look like a proper web server. We've made a lot of progress. So let's take a little break, and in the next video, we'll find out how to make our API here a little more data-driven without hard coding all of our responses for all of our endpoints. I'll see you in the next one. Bye-bye. Welcome back. The code that we've written so far, which responds to 2 different endpoints, is functional, but not very realistic. When we're writing real-life servers, we'll be sending back data that's coming back from some sort of database, where we might have dozens of different friends, and each of those friends might have their own set of friends. In our server, we need to have the ability to query for individual items in our collections, to be able to run queries and get the data that we need to display whatever it is that we're showing to the user. So when our data lives in a larger collection of data, say we have list of all of our friends, which is an array of many of these types of JSON objects. So we have Sir Isaac Newton, but we also have Albert Einstein. And for the sake of convenience, let's have one more friend so that our IDs align with the index of the friends array. So our 0th friend is going to be Nikola Tesla. How would we query this data in the browser? We would pass in, next to the name of the collection, the ID of the friend that we want to get. So for this data, it would be friends1. Or for Nikola Tesla, it would be friends at 0. The ID of the friend is a parameter in our endpoint. So you'll often hear this called a parameterized endpoint or a parameterized route, where a route is basically another way of saying endpoint. But we'll get into that more when we talk about routers and how they can help us organize our endpoints. So how do we do this in our Node code? When we check our request URL, we'll need to do some sort of additional parsing. There's really many ways that we could do this, but a quick one is to, say, create a items list where we split the URL that comes in, so request.url, and we'll call the string split method, because request URL is a string, splitting it whenever we find a /. So say we have a URL for our request, which looks like /friends/2. This would give us an items array of an empty string, because that's the first thing that's prior to a /, and then friends string, followed by the string 2. And our code is starting to get a little bit messy here, so I'm going to remove this alternate form of setting the headers. But now, rather than checking the request URL for friends or messages, we can check the second item of the items array. So it'll be the item at the 0 first index. And rather than checking for /friends, it'll just be friends. Same thing down here. Items at 1 will be messages. All right, so for our confidence, let's run this and see that it's doing what we think it should. So I should be able to get the messages and the friends as well. It seems like I'm not able to get my friends, so let's see what's going wrong there. Nothing wrong, I've just removed the JSON object, because what we really want to do here is have an additional check, where we check if the length of the items array, so items.length, if that's 3, then that means that we've passed in this extra parameter asking for a specific friend. So we're going to have one piece of logic if the length is 3, and otherwise, we're going to pass in the entire friends array. And we're going to stringify that. This is to handle requests to /friends without that additional parameter. Whereas if the length is 3, we're going to send the stringified version of friends at a specific index. So let's create a variable for that friend index, and that's going to be the 0, 1, 2, so second index of this items array, or the items indexed by 2. But remember that these are all strings, returned by the string.split function up here. So we're going to need to turn this items string into a number. So we could do this any number of ways. We could use this fancy shorthand syntax, where we add a plus sign to a string to convert it to a number. Or we could be explicit and say number, passing in that string into our number function. And finally, we'll pass in the friend index to get the stringified version of that specific item in our friends array. Does all of this logic that we're writing make sense? Looks reasonable to me, so let's try it out. First, let's see if we can get all of our friends. Amazing! We're getting this stringified JSON array with all of the data for all of our friends. And let's say we want to get the data for Mr. Einstein. So that's the ID 2. And there you go. We're getting these specific items from our friends collection. We can do this for any of our friends. Now, our code is far from perfect. I definitely don't recommend doing this in production. For example, if I try to get an index that's not in our friends array, well, the server doesn't respond. The server should probably be telling us 404 not found, because the friend with ID 4 doesn't exist. And we wouldn't go around writing a larger server where we're hard-coding the length of our URLs or the amount of parameters that we're passing in. This is more a quick proof of concept. What we have demonstrated, though, is how even very simple requests can start getting quite complicated when you need to parse the incoming request. For example, to get parameters. Now, we could keep improving our code here, but there needs to be a better way. This seems like code that could be written once really well as a package and reused in most web servers that deal with collections of data, like our friends. As a developer, it's reasonable to expect to have existing packages help us with these common scenarios. That feeling as a developer that a problem has been solved before is a very healthy sign. It's a sign that you might want to search for an existing solution and either use that existing solution or learn from it. So you don't spend time reinventing the wheel when really good solutions already exist. And you could instead be solving the problems that make your application unique. Of course, when you're learning and exploring Node like we are, it often pays to look behind the scenes like we've done here. But we'll look at some frameworks that can help make our lives easier very soon. For now, let's finish exploring Node's built-in way of working with HTTP. There's a couple more interesting things to learn from how Node does things. So let's go. I'll see you in the next one. Welcome back. Before we move on, we need to understand something important. Something that affects us every day when we browse the web. What is this? It's the same origin policy. This is something that's definitely going to come up in your career as a Node or web developer. So let's take some time to understand this often misunderstood concept. Let's start with what an origin is. When we browse the web and we go to a site like Google Maps, what we type in the browser is something like HTTPS for a secure connection, www.google.com/maps. And the origin is a combination of three things in what you see here. The first is the protocol, which is the part that says how you're communicating with the server at Google. In this case, using the HTTP secure protocol. Next up, we have a critical part of the origin, which is the host. The host tells us which server we're going to be browsing to, or which server is going to be handling our request. And the third part of the origin is the port, whenever it's included in your request. And this would look something like :443, which is the port that your browser assumes when you're using the secure HTTP protocol. Whenever one of these three things changes, we are no longer on the same origin. We can browse to other pages at that origin. So maybe we replace maps with mail to get our email, but we can't change google.com to facebook.com and still be at the same origin. That makes a lot of sense. But we also can't change the protocol. So if we go to http google.com and not https, the origin has still changed. The origin is the combination of these three things. Now, why does any of this matter to us? Well, it's because your browser and JavaScript use what's called the same origin policy. Let's explore. The same origin policy is a security feature by your browser that restricts what your browser is allowed to load when you're browsing pages on the internet. You might be browsing on your computer a site like google.com and making requests to Google servers. But the JavaScript that you're running on your browser that has Google's code might also potentially make requests to facebook.com. Maybe it's submitting a form to Facebook or getting some data about your friends. Under the same origin policy, your browser allows all requests from the same origin as the page that you've loaded in your browser. So you can be on google.com and make requests to google.com with the HTTPS protocol. But the browser restricts requests from different origins than the site you're currently browsing. So the scenario where Google gets data about your friends from Facebook isn't allowed, because that helps protect your privacy. So say we've typed in google.com into our browser and we're browsing Google. The request to Facebook will be denied by the browser because it's enforcing that same origin policy. Now there is an exception. Writes that cross origin servers, so from google.com to facebook.com, are often allowed, even with the same origin policy. Writes include things like post requests, where you submit some data to the server. These are allowed because they don't risk your data from Facebook being leaked to Google. Our page at google.com can write or send anything to Facebook, and it's completely up to the Facebook server how it responds to that request. It knows where your request came from and what it contains. It can choose to completely ignore that request if it looks like it doesn't belong. Maybe it's a request from a hacker or some other malicious site. Here's an example. Say I'm on google.com and I'm running a search for machine learning. Google will recommend me a series of links based on its algorithm. Now I can easily cross-origin from google.com to wikipedia.org just by clicking on this link. We didn't make the request from JavaScript, so the same origin policy didn't restrict us. Instead, we clicked on this link in the HTML for Google's page. If we instead try to get Wikipedia's data from JavaScript, say by going to our JavaScript console and using the built-in fetch function that our browser has in the global window object, remember that's the browser's equivalent to Node's globals, and we can use this function to pass in the URL of the server we want to fetch data from. So HTTPS, and then we're going to get the English Wikipedia homepage. This is now a cross-origin request because we're browsing Google at the moment and we're trying to get the main page from a different domain. So let's see what happens. We get this error that says that access to fetch this address, including wikipedia.org, from our Google address has been blocked by CORS policy, and that this header, access control allow origin, is not present for that request. Whoa. So what's CORS? Well, there are many rules that control which kinds of requests you can make with the same origin policy. And we've seen the most important ones in this video. But it's not a simple policy. So when you need to talk to many different servers across many different domains, it's best to make sure you're using what's called CORS, which our browser just warned us about. So what's CORS all about? We'll find out in the next video. But what we need to understand about the same origin policy is that the main idea behind it is to keep users browsing the web secure while also allowing them to make the requests they need to browse the internet and visit websites which aren't trying to steal their data. All right, I'll see you in the next one. Welcome back. So what is CORS? It stands for Cross Origin Resource Sharing, or CORS for short. It's a way of relaxing the restrictions that the same origin policy puts on us developers, so that we can make applications that potentially span many different domains and origins, because the same origin policy generally limits us in the browser to talking to just one origin. We'll start with an example. What does Wikipedia do for their site? Let's take a look. I'm browsing the Wikipedia article on machine learning. And if I go to the developer console, under the network tab, let's see what happens when I refresh this page. We can see many requests were made just for this single article. If I scroll all the way to the top here, the first request is for the main article, getting the data that we see in front of us. But Wikipedia gets much of their media, many of the diagrams and photos that its articles use, from a partner site, which is wikimedia.org. A different domain than Wikipedia. And we can see here a request was made to get this diagram of a multi-layer neural network in PNG format. Wikipedia and other websites are able to make requests cross-origin to wikimedia.org because it uses the CORS header, which we can see if we scroll down under response headers. We have access control allow origin followed by an asterisk. This is a header that's set on the server, which specifies the origins that the resources from the server, like this diagram in this request, can be shared with, beyond just the same origin that the file exists on. If we don't set this access control allow origin header, well, the default rules of the same origin policy apply. And it's only really your own domain which can talk to your server and get any data from it. But that's just not enough when, like Wikipedia and the Wikimedia Foundation, you have your content on many different origins, or you have many different APIs at different sites. This CORS header allows us as developers to allow an exception when we know requests from a different domain are safe and expected. This header is always set on the response and is controlled by the server who owns the data. So let's see what values this access control allow origin header can have. This header is optional, so our first option is, of course, not to include it and follow the textbook same origin policy. But we can also specify the access control allow origin and include a specific origin as the value of that header. So say we wanted to allow that request from Google to get the data for wikipedia.org. the same request that failed for us earlier. Well, to allow that, Wikipedia would need to set a header that includes google.com in the list of allowed origins, and then send that header back when we make that request from JavaScript. Or alternatively, we can, like we saw with wikimedia.org, set access control allow origin to allow all, or this asterisk symbol, which allows requests from any origin. You'll often see this in servers that are under development or that host data which is meant to be used by basically anyone on the internet. But in production, if you're really trying to lock down your site, it's a good idea to explicitly set access control allow origin to the list of domains that you know will be making requests to your server. Maybe you're running an online store and you know that you'll be getting requests from paypal.com for payments. You would include just that domain, just that origin, in your headers, and avoid allowing potentially malicious sites to make requests to your store, potentially interfering with the activities of your customers, which wouldn't make a great customer experience, right? The really great thing about CORS is that it follows this practice of whitelisting or allow listing, which is the practice of explicitly allowing access to some particular privilege or service, like the access to be able to read data from a server. And it's the opposite of blacklisting, where by default you allow access and you just have a specific list of privileges that you block or users that you block. When you follow blacklisting, it's really easy to miss one of the people or privileges that you want to block than it is when you deny access by default and only allow access to a pre-approved list of people or services. That's whitelisting. When it comes to security, it's always better to whitelist than it is to blacklist. And that's what the access control allow origin header does. The origins that you allow in the header are your whitelist, and you're denying all other origins. Back to our Wikipedia example for a second. The Wikimedia Foundation, which hosts this server, made the choice to allow all origins to get their data. Likely it's because they decided that access to their data is more important than securing it, which makes sense when you're hosting publicly available data. Our original request from Google and our JavaScript console while browsing our Google search results, the reason why that failed when requesting the data from Wikipedia was because this original request to the article or even to the Wikipedia homepage doesn't have any CORS headers. There's no access control allow origin anywhere here in the response. If there was, our example would have worked, and we wouldn't have gotten that CORS error. Finally, it's worth noting that it's the browser that does all of this enforcement of the same origin policy, and CORS as well. If I built a browser and chose to ignore those headers or those policies, and I convinced you to use that browser, you wouldn't know the difference. You'd still be able to browse the web, and these servers setting that header wouldn't be able to do anything about it. Which is why it's important to use browsers and other software that you trust and that you know follows the standards of the internet. And with that little message, I'll see you in the next one. Welcome back. We've looked at how to use Node's HTTP server to handle requests to get data from the server, like messages or a list of friends. But how do we handle requests that submit new data to our server? Say, adding a new friend. To submit data to our server, we most often use one of two request methods. It's usually either the post or the put method. And in the majority of servers, it's almost always the post method. Because the post method is used to add new data, whereas the put method only updates existing data. Data that's already there. And we can always replace a put request with a delete to delete the old item and then post the updated version. So some servers avoid using put entirely. Whether that's a good idea or not is often just a matter of preference. Although I say there are cases where put is the better option. Like when we want to limit the amount of requests we're sending back and forth. But post is definitely where we want to start in the majority of cases. Alright, so how do we work with post requests on the server side? Let's look at how we might add a new friend. We already have a request where we get either a specific friend or the list of all of our friends. But these are both requests where we're getting existing data. We're going to want to differentiate between those GET requests and POST requests. And we can do so by looking at the request object and getting the dot method property from it. So if it's the get method and we're getting the friends collection, we want to run our logic here. But we can add another case if the request method is post, and again, our items array is telling us that we're looking at the friends collection with the /friends in our URL, then we can complete whatever it is we need to do to add that friend. So when we handle different types of requests, we generally look at the URL, so whether it's friends or messages, say, and we combine that with the request method. So let's be explicit and say that for the messages collection, we're also only looking at get requests for that messages collection. And we're going to have to read the data that was passed into our server, which contains our new friend and any ID and name that they have. Now remember that the request object is a readable stream. So we can use a listener using the request.on function, listening for data events, which will pass our data to this callback anytime it's streamed in to our request. Because again, we read from that request and we write to the response. Now, say we want to log the data that we get back in our callback. And we'll just say that the request is whatever was passed in. But the data that Node gives us on a readable stream like request is passed in as this Node buffer object, which is a collection of the raw bytes that are being sent to us from the client, from the browser making that request. So to print out the data, we're going to need to convert it to a string. And luckily, we can do that using the toString function provided on the buffer object. Now we can print that friend data because it's now a string. Except we want to add this friend to our list of friends here, which is a list of these JavaScript objects and not strings. So let's look at our data again. We're going to be receiving data in a post request, which we can listen to by handling the data event from the request object, the request stream. And really, the data that the client gives us, let's say that's in JSON format. So there's a few different conversions happening here. The JSON that the browser is passing to our server is being received as a buffer, which we're then converting to a string, but we then need to convert it back to an object so that we can add it to our list of friends. So the last step here will be to parse that string using the json.parse function. And we'll take the object that this returns us and push it to the friends array. So friends.push. It looks like we're doing what we need to do by matching the post method, converting our data to a string to print it, and then converting it again to JavaScript object to push to our friends array. All right, so now we can run this server, but how do we test what we have? In the browser, I can open the JavaScript console and make a request from the browser by using the standard fetch function available in our browser. This is a built-in browser function that we can use like so, calling fetch on the address that we want to make a request to, so localhost on port 3000, and it's an HTTP server, and we're going to be making a post request to the /friends endpoint. So we can write /friends, and the way we tell this function to make a post request as opposed to the default, which is a get, is by passing in this second parameter, which is an object that has a method property where we can specify the method. So post, and we can also specify the body, which has the data we want to pass to the server. So in our case, let's say we're going to add a friend with the ID number 3, and our friend, let's say, is going to be the creator of Node, Ryan Dahl. So this is the data we want to pass to the server, but the fetch function expects a string and not a JavaScript object. So we need to convert our body to a string by calling json.stringify, which will turn our object over here into the corresponding string. And now we close out our brace and our fetch function, and we can try making our request. And in the server, we can see that the request was received, and the data is being logged correctly. Now we can check the list of friends that we get in our browser, and there we have it. Ryan is our new friend in good company. We can even fetch his data by passing in the ID directly. Now, of course, if we restart the server, our new friend won't be saved because we're not persisting our data to a database. It's just living in that array in memory. But the process for saving to a database would follow the exact same flow. And our browser is getting this resource interpreted as document message because generally we expect our JSON to be handled by our code and not just displayed as a document or as text directly to our user. So the browser is warning us that our application JSON type data is being handled in an unusual way. The browser is just looking out for us, making sure we're displaying the data intentionally. I know we just covered a lot, so let's take a little break and then really solidify our understanding of the way that Node handles requests and responses in the next video. I'll see you really soon. Welcome back. The final piece of our little puzzle here, and a little bit of a surprise. How would we make an endpoint that echoes back the data that the user passed in the request back to them, exactly as they had passed it? So if we send the data for Albert Einstein in the post request, the response to that request will be the exact same data about Einstein. Sounds simple, right? Or is it? With all those conversions that we had to do to get our data back into JSON in the previous video, will this involve more of that? The answer lies in how the request is a readable stream and the response is a writable stream, which means we can pipe what's being read from the readable stream to the writable stream here, and the data will flow straight from the request back to the client through the response. All we have to do is take the request and pipe it to the response. That's it. Just like in our planets project, we had the CSV file being read as a stream and then being piped into the CSV parser to get back the parsed rows of the CSV file. We can do the same thing with our request. So we pass in some JSON data in the readable stream and then pipe it into the writable stream, which is the response, to send back that same JSON back to the browser. This is the power of Node's approach to using streams. We could echo the data back, like in this flow, but we could also pipe it and stream it to another server, or process it somehow as it comes in, just like we did with our planets project and the CSV file with our lines of data, all without blocking our code. Node is very, very good at working with data in this way. Data using streams. So it was very, very easy to modify our endpoint over here to echo back the friends data that's being posted to our server. Let's see this in action. In our browser, we're going to be making a post request to our friends collection, just like we did in the last video. Except this time, we're going to be expecting a response that contains the data that we passed in. So let's take this fetch request, and we'll use that as a starting point. And we're going to add a new friend. So with ID 4, say it's going to be Grace Hopper, who was involved in the creation of some of the first computers and programming languages, like the UNIVAC computer and the COBOL programming language. This time, we're going to do something with the response from the fetch function, which returns back a JavaScript promise. So we can do fetch and then call the .then function on the result. And because we're passing in JSON into our function, we're going to need to parse the JSON that comes back from the server in the response, because we're sending back exactly the same thing. So the way to parse JSON using this function is to take the response, and this is a callback function that's going to handle that response to basically return the response converted into JSON using this built-in .json function that's part of the response object. And we can add another .then to take the now parsed JSON response, which represents our new friend. So it's going to be taking that friend, and we're just going to console.log that friend data. Now, for this to work, because we're going to be making a post request with a JSON body, and we're hoping to get back the data in the response and be able to read it, we'll need to satisfy CORS and the browser's same origin policy. To do so, we'll make sure that our browser is pointed at our web server, and that we have one of our endpoints loaded. So I'll refresh this request so the browser knows that when we're fetching, it's coming from localhost and it's a same origin request. Now, actually, let's change the ID for Grace here back to 3 because our friend Ryan Dahl got forgotten when we restarted the server, which is why we're not getting any data back in our response. We'll definitely add persistence, but that's still coming up in the course. So let's make sure our other friends are there. And let's make sure to write localhost port 3000 /friends and not /friends/, because that's another quirk of the way we're handling our URL in the server. When we parse our URL and split it on the slash, having the added trailing slash will mean our URL looks like /friends/, making the items array have 3 different items, 1, 2, 3, which means that our little parsing code here is going to get confused between a request to get a specific friend which is when we pass in that extra ID, and the request to get all of our friends. Oops, it's definitely time to find some more robust code and a well thought out framework that can help us catch all of the possible cases when dealing with something as simple as URLs. But first, let's finish what we started. I'm going to make a request not to /friend/, which just gives me one friend, but /friends, and we get all three of the great minds that we expect. All right, so we got a little bit sidetracked by the limitations of our very basic implementation. But let's see if our echo endpoint that pipes the request to the response returns the values that we pass in as we expect. All right, not the response we were expecting, but this happens. Even when you're teaching something and you've done it 1,000 times, we can't let ourselves be frustrated when things don't go according to plan the first time. Let's see what's causing our error. Now, what our code is doing is that it's piping the request to the response when the request gets this data event inside of the callback. So likely what's happening is the data event is already processing part of the request, and then we pipe an incomplete request to the response. So what we should be doing is piping the request after we register the listener for the data event, but not after the data has already come in and is already being processed by our code. And let me just add this missing semicolon. So let's run this server again. And in our browser, let's run that fetch command again. We've done it! Grace Hopper has been added to our list of friends, which we can verify by refreshing the endpoint. There she is. And we're getting her data back in the response from our fetch function, with the JSON parsed and the result logged into our console. And while our HTTP code over here has a decent amount of logic, the actual code where we work with streams and the request and the response is very, very simple. The fundamentals for Node are very, very strong. All we need is some higher level functionality to help us avoid some of these bugs that we've been making when writing our bare bones server. And before we go, there's no need to call the end function on the response when we pipe, because the response will end whenever the request ends, all using the power of that pipe and streams in Node. All right, there you have it. Our first ever HTTP server that keeps track of a list of friends, works with streams of data, and even outputs some HTML. Let's keep exploring, but for now, well done and bye-bye. Welcome back. To recap, we've learned how to create our first HTTP server that handles incoming requests and responds to them by using the two streams that Node makes available for us in the request and the response objects. We've learned how to handle different types of requests by looking at the method and the URL of the incoming request. And we've seen how to set the status code, the headers, and even write some HTML. But we've been writing code as if we were the first developers ever to work with Node. We've been doing things the hard way, without taking advantage of any of the work that the Node community has done to make our life easier, especially for when our server gets even more complicated, working with different types of data, say forms and large files, or social authentication with sites like Google, maybe more advanced URL parameters that require more robust handling than what we've done here. In order to support any type of application that Node could possibly be used for, the Node developers had to make the HTTP API very low level. It just gives us these two streams and does some very basic parsing on them to split a request and a response just into the headers and whatever we pass into the body. If we want to focus on the code for our applications, it makes sense to use a pre-built framework that gives us a little more functionality out of the box, so we don't have to recreate it ourselves. The good news is that there's a massive community of developers who've been using Node for years. And they've built tools that we can use to make our lives easier. We're going to be looking at frameworks that can save us from making the mistakes that we made in this video. And they'll allow us to make applications that are much more powerful and comparable to what we would do in a large organization, like, say, NASA. Generally, when we use frameworks to do something, the initial learning curve is a little higher. But we get so much more functionality and power as a reward. But honestly, to understand things best, it helps to have done things without a framework first, and then to understand the power that the framework is giving you, and to understand what's happening behind the scenes. That's one of the biggest differences between a senior developer and a junior developer. It's that deeper understanding of how things work and why. Knowing these details allows you to make better decisions when it comes to solving the difficult problems that come up when you're working on interesting products in a team of developers. All right, I'll see you in the next section. Bye for now.